Okay, so good evening. Welcome to today's Asset Colloquium. For some of you who are not from TIFR, Asset is a weekly colloquium where topics on instrumentation, electronics, detectors, software, medical technology, and such topics are kind of discussed. This is in addition to the two other colloquia, namely the Natural Sciences Faculty Colloquium and Mathematics Colloquium, which happens on Wednesday and Thursday, respectively. So today's colloquium is going to be given by Professor Vijayaraghavan Rajamani from Condensed Matter Physics, Condensed Matter and Material Science Department at TIFR, and he's going to speak on the second quantum revolution. Will you join it? Just to say a few words about Dr. Vijayaraghavan, we call him Vijay. He completed his bachelor's in physics from St. Stephen College, Delhi University in 1999. And then he spent a couple of more years at the University of Cambridge pursuing a BA in natural sciences before actually starting his PhD at Yale University in 2001. At Yale, he developed a new measurement technique for superconducting quantum bits. He continued this work on improving quantum measurements during his postdoctoral work at the University of California, Berkeley, which in fact led to the first observation of quantum jumps and the first demonstration of quantum feedback in a solid-state quantum system. In 2012, he joined TIFR and set up Quantum Measurements and Control Laboratory, and he's the principal investigator there. And the main goals of this lab is to develop superior quantum processors and develop techniques to stabilize quantum states against decoherence. Some key highlights of this particular group include development of broadband ultra-low noise amplifier for quantum measurements and a novel multi-qubit processor design. He's currently leading several other projects to build small-scale quantum processors with funding from DRDO, TCS, and DST, and so on. For some of us at TIFR, besides his work on the topics that I mentioned to you, is very active in various other fields, cultural activities, and performing arts and whatnot. He's a good singer, he's a guitarist, and he's there always for any of the cultural programs that happen at TIFR. And he conducts what is called conduction band. So those are his other activities when he's not working with quantum bits. So over to Vijay.
Thank you so much, Satya, for the very kind and wonderful introduction. And thank you for inviting me to this Asset Colloquium as well. I'm trying to remember, maybe this is my third or second Asset Colloquium in about 8 years. Every time Satya asks me to give an Asset Colloquium, my main problem, okay, what should I be talking about? And as always, I responded late to him, but then with somewhat of a crazy idea, which is what I'm going to attempt today. I think I've probably taken up a project a little too big for my hands, but I will try and do justice to it. What I really wanted to do in this talk is not, explain one particular thing in great detail or something which we have done in our lab and convey that to the broader community, but really tell you about this exciting, not so new now, but maybe relatively new for many of you who are not part of the main area of research. This is basically the research in quantum computing and quantum information, or in general quantum technologies. But this is being called the second quantum revolution, and I will explain as I begin my talk why it is called the second quantum revolution. And the motivation behind giving this talk was really to give an overview of this area to the entire TIFR family and the extended DE family as well, because of some tremendous opportunities which are coming up. And I feel we are not fully prepared to take advantage of those opportunities, and we should. And I hope towards the end of the talk, I'll be able to make a case why every one of you should be thinking about this at least a little bit. It might seem very disconnected from what you're doing today, but you will see that it has implications for almost all areas of research, and it has opportunities for a wide variety of scientists and engineers to actually make significant and important and necessary contributions for developing this particular area in India, and to also give contributions sort of to the overall development of this field. So let me get started. I'm going to start at some very basic. So I apologize to the experts. I just wanted to give some background on quantum physics itself, and then I will highlight how the first quantum revolution and the second quantum revolution are different, and then I will talk about what's going on in this area of quantum technology, and conclude by sort of telling you a little bit about what's happening in India, and in particularly in TIFR and the DAE family, and what should we be doing going ahead. Okay, so let me get started. I'm just going to... Satya, can you remove the co-host if possible for me now? All right. So just to remind you, the whole business of quantum mechanics sort of started with this so-called radiation problem. Essentially, people saw that when things get hot, kinetic energy, and there was a characteristic shape to the spectrum in the sense of how much energy came out at which frequencies or wavelength. There's a sample graph here. And they wanted to figure out how to explain this theoretically. And the existing models at that time, which were based on classical physics, either agreed, at long wavelengths. This very favorite question of which is asked to lots of TIFR students as well. And Max Planck came up with the formula to explain, this black body radiation curve. And one underlying assumption which he made, which was different from the understanding at that time, was that light came as, could only take energy in discrete units. And then, the Planck's constant came about then. And we now know that the energy is quantized in units of h bar omega, where h bar is the Planck's constant divided by 2 pi, and omega is the angular frequency of the radiation. In parallel, there was this whole question of whether light is a wave or particle. And this has been going on for quite some time, starting from Newton, who actually originally proposed that photons were like bundles of light. But then the whole Young's double slit experiment sort of showed that light undergoes interference, so it must be a wave. And then much later in the early 20th century, Einstein, after the the black body radiation work, was able to show that the quantized nature of the packets of photon can be manifested in this photoelectric effect, and he won the Nobel Prize for that. And this sort of really put this idea of wave and particle duality of light. But at the same time, people were also thinking about, well, if light behaves like both wave and particle, what about matter? And particularly when we go to the atomic and the microscopic regime, and then work by De Broglie, Heisenberg, and Bohr sort of again gave this idea that the matter also has both particle and wave aspects. So then this whole question was that if matter also has wave properties, then what's the wave equation which describes its behavior? And then Schrödinger came and wrote down his famous Schrödinger equation and introduced the concept of wave functions. The images shown here are sort of the sort of artist rendition of how the probability distribution of electron cloud around a nucleus are. And there were several key properties or ideas which were put forth, that you have a wave function now which describes the state of the system. The Schrodinger equation evolves it in time. You can no longer talk about things like precise position of an electron, especially when you're talking about the electron orbitals around an atom. But instead you have a distribution, probability distribution, which is given by the particular type of wave function corresponding to different orbitals, and that this probability was related to the modulus square of the wave function. And then in association with that, because it's a wave phenomena, you have a wave function, you know that wave function solutions to wave functions obey the superposition principle, which is that, you know, if you have two solutions, then any linear combination of those is also a valid solution. And that is because it's a linear wave equation. So that led to the whole idea of superpositions now, which could technically mean that you could have an electron in a superposition of two different orbitals, which now start, you know, introducing all these strange ideas. Okay, what does it mean? And then an extension of the superposition, when you talk about separated objects which were originally interacting, you have the idea of entanglement as well. And it's really these last two ideas which are important for considering the second quantum revolution. Sorry to pause here. Satya, could you please remove the co-host for me? Because every time the thing pops up, the menu also drops down and it obscures my screen. Is that possible?
Okay, just let me do one thing. Let me. Okay.
Okay. All right. So that was the development of quantum mechanics. Now, even though we like to talk about the, say, an individual hydrogen and talking about the orbitals and things like that, the experiments at that time and even the thought process at that time was only to apply this to collective systems. You know, what is the property of a solid? And this kind of development, you know, which led to the idea of developing semiconductors, gave rise to the first transistor in 1947, developed at Bell Labs. And then over the years, we know the story, you know, the things miniaturized, and then you could integrate first hundreds and thousands and now millions and billions of them on a very small packaging. And you come to the modern transistor where now in 2020, 21, the feature sizes are in sort of few nanometers regime. The role quantum mechanics played here was really to understand the underlying semiconductor physics or the band structure of these devices. So the quantum mechanics allowed you to calculate the band structures and how these devices would behave when currents and voltages were applied to them. But the idea of superposition and entanglement was not being directly used here in explaining the physics. So quantum mechanics is extremely crucial for the development of the transistor and understanding its behavior, but that doesn't make it a quantum technology in the way we talk about today, and it'll become clear in a few slides. And similarly, lasers, which also have been a very important aspect in the technological revolution, you know, in the last 50, 60 years, from the ability to read compact disks and store data and transmit data at high speeds, and having a fiber internet at home. A few years back we installed fiber to home in TIFR as well, and the fact that I'm able to do this presentation in high quality is really a resultant of all these technologies. And again, the physics of lasing is a purely quantum mechanical phenomena. And again, so the quantum mechanics explain the physics of lasers, and then the rest of the technology uses what we call now classical computing technology. And this actually has to do with how information is stored and processed. And also the fact that we are not really exploiting the ideas of quantum superposition and entanglement in some intrinsic way. Okay, and in fact, this was a big problem. Early scientists actually never believed that we would reach a time where you'll be talking about doing experiments on individual atoms. So when you reduce the size scale of your system, from say a big macroscopic solid to a very tiny nanoparticle, your band structures change, and then you go from a continuous band with some maybe a conduction and valence band to having a few energy levels, and then you can talk about populating those energy levels, right? I mean, that was sort of understood theoretically, but people never really thought that such experiments would ever be possible, at least in those days, and especially this idea that when electron makes transitions between its orbitals, it happens sort of in an abrupt sense, and energy is emitted or absorbed depending on whether the energy is going up or down in the orbital. In fact, Schrodinger himself was really aghast at these ideas, and he said this, that we never experiment with one electron or atom, and we do that in thought experiments, but when you start to apply the consequences of the quantum math to this, you get some ridiculous ideas. And he says, it is fair to say that we are not experimenting with single particles any more than we can raise its theory, I don't know, some exotic animal, I guess, in the zoo. And then, he also was very against this idea that these kind of quantum jumps, the abrupt transitions of electron from one orbital to the other was ever possible. And he said that I would be sorry if I was, that I was involved with this theory. But many decades later, this was done. And it started with experiments on individual atoms. This is a PRL from 1986 from the group of Dave Wineland, who later on went on to win the Nobel Prize in 2012 for essentially developing techniques to control and manipulate individual atoms and ions. And here what they were able to do was really detect them at that. They were not really doing any manipulations, but what they could see is that when the electron changes its level, it scattered light in a different way. And that allowed them to detect which level the atom was. And these sort of telegraphic noise is actually telling you that the electron is jumping back and forth between two electronic energy levels in a mercury 2 ion at that time. And of course, these kind of experiments have been done in many other systems. And I was lucky to be involved in an experiment using an engineered quantum system during my postdoctoral days, where we observed exactly the same kind of quantum jumps, but now in an engineered quantum system. And that technology plays a crucial role in actually measuring the quantum states in all of these systems. And this was later also repeated for photons. Now, individual photons also are highly quantum mechanical objects. And in fact, here they used atoms as a probe of the photons. So you have photons confined in a cavity, and then you send atoms from one end to the other end. And by doing appropriate manipulations to the state of the atoms, they could actually figure out whether a photon was lost or gained in these resonant cavities. And so the first experiment used light to detect atoms, and this experiment used atoms to detect individual quantas of light. And again, you get these telegraph-like signals which signal. And this is, of course, much more recent in 2007. And in 2012, both of these people, Dave Wineland and Serge Haroche, shared the Nobel Prize for this discovery. Okay, so what is now this whole new quantum technology about? It's about using a quantum system which is capable of implementing these superpositions and then using that as a mechanism for information storage. Now, conventional digital technology uses the idea of zeros and ones, and it's the same in quantum technology. But the fact is that this is a quantum two-level system. You have the states, quantum states 0 and 1, but you can also create an arbitrary superposition of 0 and 1. In general, it's a complex coefficient here. Parameterized in this way, the coefficients cos theta by 2 and e to the I phi sine theta by 2 allow you to plot this state on a surface of a sphere. Basically, the two extreme points, the poles, represent the sort of what we call the eigenstates of this two-level system. And then all other, in a particular basis, and all other points on the surface of the sphere corresponds to different values of these coefficients, and they're all valid superpositions. So there's, of course, an infinity of them ground state, excited state, some superposition, which is halfway through 0 and 1. And with these two numbers, theta and phi, you can uniquely sort of determine them. So this is the building block of almost all of quantum technology, which I'm going to talk about, just used in different ways and also physically implemented in different ways as well, because I have not mentioned at this point what this physical system is. So just like in classical computing, you can have many different kinds of storage and processing elements like hard drives, flash drives, in the old days, floppy disk, or the transistors inside your computer. Similarly, for quantum computing or quantum information processing, you need some physical systems which can store these states. And there's really a whole buffet of them now, starting from the original trapped ions, the Nobel Prize winning work I mentioned, to atoms trapped in optical lattices, even NMR. You can do experiments where superposition and entanglement can play a role, using photons as individual quantum particles with their polarization, horizontal and vertical, for example, as the quantum bits. And then any other polarization in between would be a superposition. And quantum dots, which confine like effectively a single or a few electron in a 2D electron gas, and then superconducting qubits, which is my own area of expertise, where you actually build microwave frequency oscillators using superconducting films, thin films on a chip. And essentially the quantum states are the no oscillation state and oscillation with the minimum quanta that is allowed by quantum mechanics as the quantum state. So there are a whole variety of physical systems, each with its own pros and cons. And you will see some of the things which have been done in the coming slides, right? So at this point, I just wanted to introduce the 4 broad areas, right? And one of the reasons this talk is challenging for me is that my own expertise lies in quantum computing and simulations, particularly in development of the hardware. So I will try to explain the other topics as well as much as possible. So quantum computing and simulations is one of the main ones, but you also have quantum communication. We're talking about having secure communication, which are protected by the laws of quantum mechanics. A very important field which is emerging rapidly is quantum sensing in metrology. So here you're developing new kinds of sensors which exploit this idea of superposition and entanglement to give you that extra edge. And then finally, a very broad area of quantum materials, which is in some sense connected to all the other 3 areas, but also has been emerging as its own thing. And these 4 areas are roughly how most quantum programs around the world are sort of divided into. Okay, and there's a lot of interlinks between these areas, but sort of roughly the purposes are different. The requirements on the technology and the quality of the technology can vary from different areas as you go. And what I'm going to do in the next part of the talk is go through these 4 areas fairly quickly and hopefully give you a flavor of why this is really exciting. Okay, so for quantum computing and simulations, this is sort of the most talked after field. You basically need a collection of qubits. So the idea I'm trying to show here is that if you have a qubit, you have these 2 states, 0 and 1, and you can create a superposition of these 2 states. So there are 2 states you can simultaneously superpose. If you go to now 2 qubits, each of them can be 0 or 1, or together, just like a 2-bit classical system, you have 4 possibilities. But the new possibility here is the fact that you can actually create the system in a combination of all these 4, a superposition state of all these 4, right? And this scales as 2 to the power n, where n is the number of qubits. The moment you introduce more than 1 qubit, you also have these special states. For example, if you have a state which is a combination of 0, 0 and 1, 1 only, then it's actually an entangled state. You can no longer talk about individual systems anymore. It represents a collective property, which it retains even if they're physically separated. For those who are familiar, this is the famous EPR paradox, which Einstein was very unhappy about, because it seemed to imply that the properties of 1 qubit, when measured, immediately determine the property of the other partner, irrespective of where physically it was located. Now, in general, a quantum computer or a quantum simulator would be a collection of large number of qubits. I mean, it could be arranged in a 2-dimensional grid like that. Here, I'm sort of showing these qubits as little small spins, because that's one way of implementing qubits. And in general, what you want to do is have a large collection of qubits which are stable. Then you want to be able to control any one of them depending on what you're trying to do, and then also create interactions between them. And there, the whole question of how the physical systems are laid out, what is the physics of their interaction, determines whether you can easily create an entanglement between this qubit in this corner and this qubit in this corner or not. And these are some of the choices people are trying to figure out these days. But to give a rough idea of even a modest number like 300 qubits, if I now start counting 2 to the power 300, this is an enormous number. And this is, people often use this 300 qubits as a reference. This number, which is the number of different states you can superpose at the same time, represents roughly the number of atoms in the visible universe. So let me emphasize this again, 300 qubits, you compare that with 300 bits, it's sort of an insignificant number of bits. Your phone has gigabytes of RAM. Each gigabyte is 1 billion bits. So a very tiny number of qubits can give access to a space, which is sort of this, which we call the Hilbert space, where these operations are being done, which is massive. It's 2 to the, and basically there is no way you can handle this kind of a quantum system on a regular computer, right? And I will make a comment on that in just a little bit. And in fact, that was the idea. In fact, one of the ideas which sort of pushed research in this area was when Feynman had sort of pointed this out, that doing quantum mechanics on classical computers is very hard, because you essentially have to represent these 2 to the 30 states if you want to really do a computation involving 300 qubits. And it's not a lot. There are lots of physical systems which would easily require much more than 300 qubits to describe them correctly using quantum mechanics, right? So any molecule with many electrons in them, many orbitals interacting, for example. So this is the idea which Feynman had, that, well, why are we using like doing a mapping from the quantum mechanical equations on a physical system which uses different laws for computation? And his idea was that, well, let's just use the same a system which follows the laws of quantum physics, which means that if you are trying to understand a physical system which can be represented by, say, 300 qubits, then don't use 2 to the 300 things on a classical computer. Use a system with 300 qubits. Of course, the answer is not that simple, because these qubits have errors and things like that. And the general idea is that any quantum 2-level system is sort of equivalent to another 2-level system. So you can mimic the behavior of one quantum system, which is hard to maybe experiment directly with, or you want to just understand what might happen in some unpractical situations. Then you just use some other physical system which you have in your control and make it mimic the behavior of the system you're trying to understand, right? So that's why these are called quantum simulations. It's one of the most interesting and probably widely anticipated applications of quantum technology, especially for scientists and engineers, because this would allow you to do many, many analysis, which is currently very hard.
Experts can I ask a question?
Yes.
Vijay, can I ask a question, Vijay?
Yes, please.
Is it okay?
Yeah.
Different complicated systems essentially have different types of interactions. So how would you take that type of complexity into account when you map it into the type of qubit system that you told?
Yeah, that's a very good question. There is no simple, obvious answer that there is some mapping to for every problem out there. And this is part of the challenge in developing that mapping and developing that algorithm which would allow you to do the simulation. Now, some basic interactions are possible between these physical systems, and that would also depend on the choice of the few physical systems you have, that which type of interaction is easy. For example, the most common interactions you can create with these qubits are dipole-dipole type of interactions, but others are also possible. And quite often there's actually an effective mapping done. Even like, for example, you could do fermionic calculations, but using only sort of bosonic kind of systems. People have figured out some mapping. Sometimes they're not very accurate, but other times the mapping is exact. So you gain by doing that. But yes, there is no generic formula for doing this for any arbitrary problem. And this is an active area of research where physicists and computer scientists have to work together to develop the right mapping, and then also figure out which physical system to use, because there are a handful of them available right now, and they all come with their own sort of pros and cons. And a quantum simulator in that sense is could also be a custom device, unlike what is called a universal quantum computer. It's just like you don't need different computers for word processing and playing games. It's just the software which changes. It's once you have a universal, what is called a universal quantum computer, just by changing the software, you'll be able to solve different kinds of problems. But that is still, quite a distant away. But you could build custom sort of hardware which allows you to simulate specific problems. So you sort of design your hardware to tailor to a particular problem.
Thanks.
So I already mentioned this, that if you have n qubits, you can create a superposition of 2 to the n possible states. And in general, your quantum algorithm, which is sort of acting on this collection of qubits, essentially changing their states, to be sort of mathematically precise, we're doing what are called unitary operations. It takes the initial set of states and maps them into a set of new states. And it has to do that in a very specific way, so that once the computation is done, the set of manipulations are completed, and you go and record the state of all the different qubits which you had, which, remember, because of the quantum measurement postulate, will only give you the answer 0 or 1, because it will always give you a binary answer. So it might seem strange, but an n qubit system at the end will only provide n bits of information. So you really have to use the fact that these are wave functions, and there is ability to create these superposition states, that during the process of this evolution, which we call the quantum algorithm, you sort of destructively interfere all the wrong answers and constructively interfere the system towards the state you're trying to push. I mean, this is a very simplistic picture of what a quantum algorithm in general does. And just like what Spenta asked, in general, for coming up with a quantum algorithm for any problem, there are no formulas or algorithms for that, where you say, okay, I just put this in and out comes a quantum algorithm, which might or might not be better than the best classical algorithm for solving that problem. So this is, again, fairly non-intuitive, how to use the idea of superposition and entanglement and make it work for you in order to get an advantage. But of course, people have done that for several important problems. And one particular problem is related to the idea of searching, search within quotes. So imagine you had a deck of cards, and there is, let's say they're all unique, and you are asked to find out one particular card, which is, say, 7 of hearts, right? And so whether this problem is done by a human being or a computer, there is really no other way than just picking, opening the cards and seeing, which card it is. And if you are lucky, you might find it in the first shot, or if you're unlucky, you might find it in the last trial. So on an average, if you have, 2 to the n cards, which can be represented by n bits, then you need to go half the number of such trials to find the right answer. So this problem, in the context of a quantum version of this problem, is that you have a quantum, you have this black box or oracle, which basically does the selection of the state. And it basically tells you that if you send in the chosen quantum state, which 7 of hearts in this case, then it will change the sign of that wave function. So otherwise, it will just return it in the same way without doing anything to it. And what Love Grover showed in 1996, that if one implements a quantum algorithm for identifying this special state, which is sort of encoded in this black box, you only need roughly square root of n steps rather than n by 2. So there's an advantage, as n becomes larger and larger, square root of n gets smaller and smaller compared to n by 2. And, just sort of a cartoon way of representing it here is that all these vertical bars represent sort of the weight of the superposition. So you have some number of eigenstates, you create all of them in an equal superposition. And then as the algorithm proceeds, the oracle will flip the sign of the special one, and then the algorithm will actually act in such a way that it amplifies the probability of that particular state only and suppresses the probability of all the other states. And in roughly square root of n such steps, this peak basically comes close to unit probability, and all the other ones sort of get suppressed close to zero probability. And these kinds of problems are very easy to verify, that once you find an answer, it's easy to check whether that's the correct answer or not. And Lovegrove was able to show that you need approximately square root of n steps. So it was an advantage than the best classical way of doing this algorithm. Right? The other famous algorithm is the Shor's factoring algorithm, which is related to finding prime factors of large numbers. So here are two prime numbers. You multiply, creating the product. This is easy to do. It turns out the reverse problem is very hard, especially if this number becomes bigger and bigger. And this hardness of this reverse problem is actually behind an encryption scheme called the RSA, named after the three people who invented this. And it relies on this hardness of the problem, the fact that no powerful computer on the earth can actually solve this reverse problem, so your data is secure. And only the person who knows these two keys can actually decode the problem. And what Peter Shor in '94, so 2 years before the Grover's algorithm, showed that there is actually a version of this you can implement on a hypothetical quantum computer. It's not built yet, but if it follows all the laws we expect a quantum computer to follow, then the problem can actually be solved. Essentially, the amount of time it takes to solve this problem in a conventional computer grows exponentially with the size of the problem, but in a quantum computer, it was able to show that it only sort of grows polynomially, so much slower, and hence you can have some crazy result, like if you have a 1,000-digit number, it would take 10 to the 24 years, essentially impossible on a classical computer, versus something of the order of 10 or 20 seconds on a quantum computer. Right? We don't have such machines which can do this just yet. And so this also, these two algorithms actually really pushed the development of the hardware. Till that time, there was not sort of a very strong effort on actually building machines which eventually would be able to implement such algorithms. And that really set the ball rolling. And I recently came across this YouTube video by Peter Shor, where he sort of recounts the history of how the Shor's factoring algorithm came about. And it's sort of people who like history of science. And he's an interesting character. So I would recommend just taking a look at this video when you get a chance. And this, of course, also worries people, that because a lot of our current encryption, when we communicate on the internet or do ATM transactions or credit card transactions, they all rely on something like the RSA encryption. So one might wonder that if a quantum computer is developed, then you are sort of in a risk of losing all the security. So this has obviously has attracted the attention of the defense and the government in throughout the world. Coming more to the using these for sort of quantum simulations and doing science. Experiments from few years back showed that you can actually use a quantum processor to do certain kinds of problems. So these are actually toy problems right now, but they sort of demonstrate the idea that once scaled up to a large enough number of qubits, because it's the same problem. When the number of qubits are small, it's a simple enough system that it can be represented efficiently on a conventional computer. And these are talking about finding the bond lengths and how energy varies as two atoms are kept at different distances to find the sort of the bond length, which is the minima of the energy, using a quantum computer. And more sophisticated versions of these calculations become very, very hard, because you cannot describe the problem fully using quantum mechanics. And these were done using the superconducting based quantum processor using some 5 qubits. And they actually got some, so the dashed line here are the analytically calculated curves, because these are simple systems. The The other colored dots here, the red, yellow, red, are the calculations done without sort of taking into account the errors which keep happening in these qubits. They were able to do some error mitigation, and then 2 years later, they were able to sort of make them line up on that. These are currently not of practical importance, but a lot of work is being done, even in industry, to see if these techniques can be adapted to solve some real-world problem which could be used. And as I said, this will all become much more important and relevant as the size of the problem becomes bigger and we are able to actually implement them with fewer and fewer errors. Something sort of connected to biology, maybe with photosynthesis. I don't know exactly whether it's biology, but it does play a role there, where they were able to study these so-called light harvesting models, like how when a photon hits, say, a chlorophyll molecule, how is it converted into excitations and then sort of the rest of the chain reaction. And there is some interesting role of the environmental effects which play here. And they were able to model this by sort of scaling down the problem by a factor of 10 to the 5, sort of mimicked on a superconducting processor. And they were actually able to demonstrate that usually environmental noise, which is considered a bad agent in all quantum calculations, actually played an important role in actually having that process work out. So these are just some samples of the kind of quantum simulation and quantum algorithm things which people are doing. And there are many more and many more to be developed as well. And this, once you are able to do this, then you can essentially sort of simulate chemical reactions. You can make new medicines, study their interactions without ever having to test it. I mean, this is sort of how I imagine it would happen. There's a lot of work on doing high energy physics simulations using quantum computers, and many of these will actually involve hybrid algorithms where part of the problem will run on a quantum machine, and the rest will run on a conventional classical computer. Coming to sort of non-physics side, but sort of things which are relevant to the industry, image detection, logistics and routing. Traveling salesman problem is a well-known problem about how to send your FedEx delivery guy on the right path so that fuel costs are minimized. And this is a huge money saver for companies which deliver things all across the world. And there are no efficient classical algorithms to do that. So when people are trying to see if quantum versions of these algorithms can do a better job, and now industry is trying to use these small scale quantum processes which are sort of around now to work and use these things for developing practical applications. Right. So in the field of computing and simulations, we have sort of small scale processes available today. Google and IBM are two big players which make these things out of superconducting circuits. As I mentioned, these are microwave frequency oscillators, essentially, which store and process quantum information. Here are some images of some chips. There's a company called IonQ, which uses trapped ions to do the same thing. And many more companies have now come in. Honeywell is working with trapped ion computers. Quantum Circuits is superconducting. D-Wave and Rigetti are also superconducting based things. And many of these small scale processes are actually available for anyone for free via cloud access. And there are various platforms. IBM Q was the first one to be launched, but now Amazon has their own thing. Microsoft has their own thing. And different hardware developers are tying up with these cloud-based service providers to give access. And you can just go and sign up, and you can get like maybe 5 up to 20 qubits systems for free. You get limited time on them. But then IBM and other companies have more specialized programs for if you want to like invest a bigger amount of money, then you can get access to larger machines, maybe up to 50 qubits, and more is coming. Just one point to make is that all of these computers don't use a technology called quantum error correction, which is still being developed. And this is basically the idea that these qubits are stable. Just like an electron in an excited state will decay back to the ground state. That's a terrible thing if it's being used to store information. Because, sorry, was there a question? Sorry. And this happens, and all of this happens in all of these qubits at different time scales. The phases get scrambled because of noise, and all these applications today are designed to run in a very short amount of time so that these errors are not very large. But theoretically, we know that error correction is possible, where even though the individual physical elements can undergo these errors, the overall information actually doesn't get destroyed. And it's a very important milestone. And in fact, just 2 days back, I saw a paper where they have demonstrated quantum error correction using a trapped ion processor, where the performance is really quite good, and more will be coming. And so it will be a very important step for making these technologies really practical. Okay, and some famous results which many of you might have heard, in the news, was this whole thing about quantum supremacy. About 2 years ago, Google, with their 53 qubit systems, which roughly represents state space of 10 to the 16, which is roughly 2 to the 53. And it was the first claim of performing a computation significantly faster than the best classical version. According to them, 200 seconds versus 10,000 years. It was controversial. A lot of people claim that this 10,000 year number is not really correct. And this is really sort of not a sort of a practical task. It's a sort of a made up mathematical problem just for demonstrating that there can be these vast differences when you use a quantum system versus a classical system. And it's really just taking the output of a random quantum circuit. A random quantum circuit is basically a random quantum algorithm where you're just doing random things, and then you want to predict the output. If you try to do that using a classical computer, it's very hard because of the same reason, that you have to store lots of things. And they use supercomputers to sort of make an estimate of how long it would take. And then more recently, last year, a new paper came using actually photons as qubits, and solved a similar problem called Gaussian boson sampling. It's not exactly the same. And here the improvement was even more dramatic. It was 200 seconds versus 2.5 billion years, with a much larger effective state space. So these are sort of now, some people have compared them to Bell's inequality type experiments, where each year there's going to be a slightly better one, and then you sort of reach the regime where you can truly show that for a practical problem, a quantum processor will be much, much superior than any classical version of the algorithm that is present. Okay. So that's the story for quantum computing. Maybe I can quickly pause here if there are questions. And I also forgot to mention, I think Satya also mentioned, that this talk is going to be a little long because there's a lot of ground to cover, but I will try to finish in another half an hour. Are there any questions?
We don't see any here, unless the Zoom participants, if you want to ask, please unmute yourself and ask the question directly.
Okay. I will move ahead. So the next topic is quantum communication. The cartoon here sort of generally is depicting a very general communication scenario, or a secure communication, where two parties, Alice and Bob, are trying to exchange some information which is secret. They don't want other people to know about it. But there is a third person, an eavesdropper, Eve, who's trying to get access to that information. So the whole idea behind secure communication is how to do this so that you can be guaranteed that your data you have been exchanging has not been tampered with, or has been copied by some other person. The idea here is to now use quantum mechanics to give you that guarantee, right? And usually secret communication of this is actually based on only a random secret key. You actually don't have to make the entire information sort of unaccessible, except that you have a secret key or a password. This is like the rule you have come up with. Maybe you have replaced all the alphabets by numbers, to give a very simple, dumb example. But as long as you, Alice and Bob, are the only two parties who know, it will be hard for any third party to differ. And there are different ways of showing which kind of codes or secret keys are more effective. And so the task comes to actually setting up this secret key, right? I've heard stories that in the army and the military, there's actually somebody physically is carrying a briefcase from one location to another, which is guarded by people to exchange that secret key. And it has to be done periodically, because if you exchange many messages which are being intercepted over and over again, then it's possible to recover the secret key and break future communications. So here the idea is to establish the secret key only but now guaranteed by the laws of quantum mechanics. And this sort of very roughly speaking comes from the fact that any attempt to measure a quantum system by Eve, because now you're going to use quantum systems to exchange information, will have an impact. It will disturb the system, and then you can know that this has been tampered with and you throw away that key. So till you are guaranteed that you're established a key which is not been tampered with, you keep doing it. And then once you have it, then you can encode your information using that secret key, and then no one will be able to decrypt it, at least for a short amount of time. So often these keys are changed periodically, right? So how does one do that with quantum systems? There are a couple of, actually there are many ideas. There's a most famous one, it's called the BB84 protocol. I want to thank Professor Urbasisina for giving me this slide. And here you basically use photons polarization states, and you send them across, and you sort of do measurements along different bases. And by doing a careful choice of the measurement basis, you can basically get a string of keys depending on the results you have received. So they actually communicate the results of these measurements over a classical channel. So even if the person is eavesdropping, and then if somebody interferes, they will know by looking at the correlations of these measurements. So then they can discard that data. So this is one particular way where you just need the ability to create these superposition states. So the superposition plays a role here, and the fact that you cannot clone quantum systems. There is something called a no cloning theorem, is that if you have a quantum system whose state is unknown, there's no way to create a perfect copy of that system. So this would be a mechanism. If it was possible, then you could copy it and keep it and then send it along as though to indicate that nothing has happened, like there's been no interference. That is not possible from the laws of quantum mechanics. And you can't divide it. You cannot take the photon, a single photon, and then split it into two, and each one will give half information or something like that. That's also not possible. So these two things are sort of guaranteeing the security of the secret key. And similarly, there is another the protocols which use entangled sources of pairs. So there's now a central source of entangled photons. So it sends photons to both sides. And then Alice and Bob will basically do, again, certain types of measurements, and by using these random bases, and that allows them to establish a key. And basically, the violation of the Bell's inequality sort of guarantees you that, yes, these are entangled, they have not been interfered with, and somebody interferes in the middle, it will show up in the measurements. So these are some common protocols. There are, of course, several more. And again, this was a result from a few years back, which I'm sure many of you have heard on the news, where they were able to demonstrate this by using a satellite. So here the source of entangled photons was actually on the satellite, and then it sent one part of the pair to two ground stations, and they were able to verify that they could do this entanglement. And the main point here is that even though the photon traveled a long distance, the entanglement still survived, and they were able to establish this thing. And this was sort of the first such demonstration done by China in 2017. The satellites, the locations on the ground were separated by 1,200 kilometers. And they were able to show that this allowed them to set up a link whose efficiency was orders of magnitude higher than if you had a fiber which was that long, so running the full length of back and forth between them. So one of the problems is that fibers are often lossy, and the loss essentially will eat your photons, and then you will not be able to do communication properly. And more recently, building on these technologies, just earlier this year, China announced that there was this world's first integrated quantum communication network. It include shorter optical fiber links so that you don't suffer from losses, and two ground to satellite links covering a total distance of 4,600 kilometers. And the results were shown in this paper as well. So China has been a major player in doing this. Work is happening in India now in ISRO, and Professor Urbasisina from RRI have projects, and some other projects which are also there. I'll mention them in a bit. Okay. Now, coming to quantum sensing and metrology, you might think that, okay, this is some exotic new thing, but actually you're aware of some of these technologies already. The LIGO can be considered as an example of a very sensitive detector, which uses interference of light as a way to very sensitively detect distortions in space-time set up by gravity waves, for example. And also magnetic resonance imaging is underlying physics is NMR, and and that uses similar idea of basically how the quantum coherence properties change if between a diseased cell and a normal cell, and you're actually just measuring the coherence of different parts of the cells in your brain or other parts of your body, and those variations allow you to detect the thing. A big challenge here is that in order to set up these effective qubits, you have to apply a very large magnetic field to create sort of a splitting which is big enough and to give you big enough signal. And what's going on is that now newer technologies are coming in. Now, in general, the idea of sensing is sort of based on the idea of estimating a quantum parameter, which affects the superposition state. So this is typically called a Ramsey experiment. So remember the block sphere picture. You start these zeros and ones are on the poles. You now create a superposition state, which is on the equator. And then any perturbation, the signal you're trying to sense, for example, if this was a qubit made by Zeeman splitting the electron levels, then the rate at which it precesses, like the phase accumulates, will change. And by doing a second pulse, you can create an interference condition, and that will change very sensitively to even very tiny amount of magnetic fields. And then basically you are then limited by how frequently you can use this measurement. So there's sort of like a short noise type of sensitivity. You can then build upon this. The central idea, as I said, is to make a superposition and measure the field through the phase which is accumulated. You can build upon this by now adding more qubits, and that sort of gives you a square root of n scaling, or you can integrate for longer. And then you can also now go beyond what is called the standard quantum limit by preparing exotic states of this collection of qubits. They could be in some special entangled states, and that allows you to improve the signal to noise ratio better as well. So this is sort of a very generic idea, and this can be implemented in various physical systems. And one particular such system is creating these qubits in actually defects in diamonds. These are called nitrogen vacancy centers or color centers in diamond. The reason some of these diamonds have this sort of pinkish glow is because of a nitrogen vacancy, where two of the carbon atoms are replaced by a nitrogen atom and one by a vacancy, which means there's nothing there. And this effectively creates a qubit-like system which responds to magnetic fields. And you can control this using optical light, because even though this qubit energy splitting is in the microwave frequency range, there are much higher levels which are in optical, and you can use like various kinds of Raman processes to excite them and manipulate them. And this has been...
Vijay, I have one question.
Yeah.
Yeah, so in these defected materials, so let's say 200 micron size particle, we'll have say thousands of these vacancies. So how do I define the qubit? Is it like a one vacancy equivalent to one qubit, or 1,000 together becomes the one qubit?
So that's a good question. It depends on what you are doing. So if you are doing, if you want to do quantum computing, where you are trying to control each individual qubit and manipulate it in a particular state, then of course this doesn't work. There you have to implant the nitrogen vacancies very specifically in particular locations and do that. And that is something which is happening using this platform, but not, it's quite challenging. So that's why the application in the sensing is much more common using diamond. And because it's sort of like, you can think of this as NMR, it's a collective thing. You have lots of qubit, you apply some pulse. It doesn't work perfectly for all of them, but it will give you some global polarization and changes, and then you detect it again. So here you're actually doing sensing with an ensemble of these spin half systems in these systems. But you can also engineer a device to really implant one defect in sort of a localized region and use that as well.
Okay.
So that's why I had mentioned earlier that yeah.
Sorry, just following up on Vivek's question, how do you do site selection for addressing just one thing that's doped in a big lattice?
Well, if you are actually able to implant, you can do that by masking and basically creating the implantation and keeping the probability low that the likelihood of having two defects very close to each other is very small. Often this is done by random chance as well. I mean, of course, this is not my core area of expertise in terms of the fabrication things. In fact, recently Sushil Majumdar has been trying to do this in TIFR in collaboration with I think Professor Trivedi. So maybe Sushil, if you are there, do you want to say something about this?
Yeah, Vijay. So basically, it is based on the beam currents where you have a very fine, a very low current that goes in and implants these ions at a low height from the surface. And what people have done now is they have started nanofabricating the diamond interface and then using various techniques of focusing the ion beam so that you have a probabilistically only one ion hitting a local pillar on the diamond surface. That's how they're getting more like deterministic single sources.
Yeah, but often you have to try again and again, and then you might get one or two good samples, at least for now.
Yeah.
There are people working on trying to do this in a much more deterministic and more highly probable case. But for sensing applications, the requirements are less stringent, and that's why the Diamond X system has become a very important thing in the whole sensing and not in the computing part of the technology.
Vijay, I have one follow-up question where why do I need a one defect? What will happen if I have 1,000 defects and all of them are behaving the same, right? You can manipulate them by some light, microwave or something.
Well, absolutely. I mean, you can. For sensing, yes. For computing, it becomes a little bit more tricky, but NMR quantum computing sort of work like that. It becomes difficult to scale after some time, because normally when you're talking about lots of these defects, all of them are doing the same thing. When it comes to computing and algorithms, then you don't want all of them to do the same thing. You want each one of them to be doing different things the way you want it. But for sensing applications, so it's just like you have many sensors now. So that's what I've mentioned also, is that you can now have n qubits, and even if they're not all perfectly the same, it still works to some extent because they will coherently add and give you some enhancement. Okay, so this is this is a very interesting platform, and there's lots of sort of things which have happened, building quantum optical networks using the Diamond platform. One of the big advantages of this Diamond-based system is actually operation at room temperature. And some people find it in superconducting qubits, you have to cool them down to very low temperatures, and there's a very good reason for that. But here, because of the combination of the optical levels and the microwave levels and the ability to do Raman-like processes using the optics, you can actually do the experiments at room temperature. I mean, even though you are doing some kind of effective cooling, it's not bulk cooling. So it makes things simpler for sensors and other applications. Of course, it makes it quite sort of attractive. And there's a lot of effort going towards making sort of molecular scale and nanoscale MRI type of detection techniques. And there was very recent work which came out in March, but I'm sure many of us here have heard the talk of Ashok Joy, who gave a talk here a couple of years back talking about some of these works, is really using these optical techniques to achieve what is called hyperpolarization, right? As I mentioned earlier, in MRI, you have to apply this huge magnetic field to polarize the spins in one direction. And the magnitude of the field makes the technology sort of complicated and hard, because you need a big magnet and you need superconducting magnets. And here, just by using lasers, you are actually able to polarize them much more strongly, sort of using the quantum physics of the multi-level system. And you get a huge signal. I mean, I remember hearing the talk here, and now this has been recently published, that this hyperpolarization by using optical techniques allows you to do both optical imaging and MRI at the same time. And this work was published very recently, and it's been making a lot of news. So this is one really powerful technology where you could imagine sensors being injected in liquid and sent inside bodies, and then you can image them externally to see what's going on. The possibilities seem quite exciting. And
Vijay, So in this case, you would still be using some sort of a detection, like still going to be relying on the external magnet, or you just have a CCD kind of detector in detecting the signals?
You can do both. So the thing is, the hyperpolarization basically gives you a much larger signal even in a conventional technique, because you just have much bigger polarization signals. But you could also just detect using laser based measurement techniques as well, because the same thing allows you to detect the state of these different spins. And again, depending on the setup, depending on what you are trying to do, what kind of imaging, different modalities would probably be.
But you wouldn't need the external magnet in that case.
Yeah, you won't.
Oh.
Yeah, for polarization. That's the sort of the long-term goal, to get rid of, or you might just need a smallish magnet. You won't need like several Tesla or of field, which then makes the requirements much less stringent. Another area where for sensing is actually to use atom-based sensors. Again, the idea is very similar. You create atoms in these sort of superposition states, and you can then perform interferometry. And this is again something which came out of the UK Quantum Technology Initiative, where these kind of portable magneto-optical traps, where you're trapping these atoms and then doing interference experiments, can be very sensitive to small changes. And there's a lot of applications in civil engineering. You can detect changes in gravity or like microgravity changes. And they basically all rely on the fact that you can have these very precise clocks. So the transitions are very, very narrow. And this is another direction of using atom-based sensors for doing experiments, which have lots of commercial and fundamental physics applications as well. So coming to the last part, which is the topic of quantum materials, I would strongly recommend you to look at this review. In fact, my slides are based off this review, and it really talks about the material challenges for all these different platforms which I've mentioned. There are all kinds of problems which are related to material science. And in this particular review, they are focused on 5 sort of important platforms: the superconducting circuits, the quantum dots or semiconducting qubits, color centers, which is basically the diamond stuff, trapped ions, which I mentioned, and also topologically protected systems. These are like Majorana fermions based systems where there is some intrinsic protection against noise because of the symmetry of these structures. And they have really gone into details and talked about in each particular platform, where is the sources of noise, where the quantum information is stored. For example, in superconducting qubits, because these are microwave oscillators, thus the dielectric loss of the material on the substrate on which you are putting it makes a difference, because that absorbs energy. You can also have quasi-particles, which are basically unpaired electrons in these superconductors giving rise to loss. But how do you do anything about it? There are these surfaces which have to be controlled and grown carefully. And similarly, for all the other platforms also, you have these kind of problems. They have gone into the details of these 5 platforms and talked about what are the different challenges which have to be solved, how do you look at interface physics. So this is now a completely heavy on material science kind of thing which is required for taking these devices to the next level. And the field of topological qubits is still, using things like Majorana fermions is still very new. And I'm sure many of you know that the original claim for discovery of observation in the Majorana mode was retracted recently. So this is really completely open. And in the last part of the talk, when I'm going to talk about the Indian context, I think this is a huge opportunity because we have such a history of strong material science, both in TIFR and in the rest of the country. And there are lots of very interesting and important problems which would allow you to take this to the next level. I mean, just to give an example, my work has not focused on the materials aspect at all, because that's not my core area of expertise. We've just started looking at some of these things in collaboration with other people, and we would love to discuss this, with and look at new kinds of materials. And so this means it's not just physics. We're talking chemistry as well, and we're looking at surface physics and interface physics. This is and also huge scope for theory and modeling as well in here. So in the last 10 minutes, I just want to give you a brief overview of all these exciting developments which have been happening around the world. what's happening in India and what's going to happen in the near future, and what should we really be doing as, say, an institute or an extended DA family. Okay, I sort of roughly divided into pre-2010. Some of these numbers are not probably very accurate, but the early work in quantum computing or quantum technology was actually in NMR, and Professor Anil Kumar at IISc Bangalore sort of led many of these experiments and demonstrated simple algorithms on small number of qubits. There were also early experiments, not published, but I've heard it from other colleagues that Professor Vasant Natarajan had done some explorations in trapping ions. There's, of course, trapped ion type of experiments being done in the group of Professor Sadiq Rangwala, and Saurav is here now, who worked in their group. The techniques are similar, but the precision and the quality of the devices required for the quantum application is different. And of course, we do all kinds of ion and collision physics even in TIFR, but they are not directly suitable for the kind of experiments you need for quantum, but they're definitely adaptable. And of course, we had the Bose-Einstein condensation type of experiments done by Professor Unnikrishnan in TIFR. And quantum condensed matter experiments have been going around for quite some time, and we have lots of experts around the country, both here. And theory efforts were also there, sort of scattered, and maybe focusing more on fundamental physics and foundations of quantum mechanics, and less so on applications. That has changed in the last 10 years. There are now several groups in superconducting qubits. Ours was the first one in India, but now we have 2 more in IISc Bangalore. Lots of groups working on QKD experiments. The group at RRI sort of leading the way with collaborations with ISRO, but also a big effort from IIT Madras, which has now also spawned a company where they're trying to develop QKD solutions. Experiments involving cold atoms in optical traps and trapped ions, semiconducting qubits, and all these things, and even development of quantum algorithms in TIFR itself. And some new theory groups have also emerged. Now, many of these were, of course, individually funded groups and labs in a scattered sense. But in the last few years, there's been a huge array of new funding programs which have also come in. And that has really kickstarted some of these things. Yes?
There is just a question. I don't know if it is a contextual one from Professor Datar.
Professor?
No, I can ask it at the end of the talk. That's okay.
Okay. Yeah. And really big one, which is sort of recently sanctioned, is the Quantum Enabled Science and Technology Program, or QUEST, by DST. And it has funded about 50 projects for 3 years with a total sum of about 200 crores. The bulk of the funding was actually released last year in the middle of the pandemic. So things have been moving slowly, sort of in an overall sense. But it really has allowed many groups to really get into this in this field or expand their expertise, and we are also part of this effort. MITI has been funding sort of centers of excellence in quantum technologies. It's a collaboration between IISc and RRI, which was again set up last year. There is a national mission on interdisciplinary cyber physical systems, and within that, there's actually a quantum sub-program. And that program was for establishment of a quantum hub, and which was awarded to IISER Pune. Again, I think sometime last year. It's a 5-year project with roughly 180 crores of budget. I've tried to give the numbers wherever I'm aware of it or through public domain information. This again, is coming up now. There is a Center of Quantum Information at IIT Madras, been around for some time. The DRDO actually started this whole series of young scientist labs in various strategic areas, and they identified quantum technologies as one. They're currently based out of DIIT Pune, but they have sort of distributed collaborations in various parts of the country, including us in TIFR. There's a big quantum experiments with satellite technology, also called QUEST, which is a collaboration between RRI and ISRO. It's an effort to set up these satellite-based links. And I think it also involves a collaboration with Institute of Quantum Computing in Waterloo in Canada. Then more recently, the Indian Institute of Science, Bangalore started a quantum technology initiative. They sort of brought together 40 scientists under this umbrella and have initiated activities earlier this year. And there's been a plethora of new seminar series. There's an MTech course voted by IISc. There are new startups which have started coming up in India as well. And the big daddy of all of this, of course, is this national mission on quantum technology and applications, which I'm sure many of you have heard about. It was big in the news. There was a major announcement in the budget last year in February 2020, where the government expressed interest to have this mission for 5 years with a budget of about 8,000 crores. And it will cover a whole range of types of research, from basic, applied, directed, translational, human resource development, including new faculty hiring, significant industry and startup contribution. I was part of the team which drafted the DPR, though it's a confidential document, so I'm going to only talk about things which are there in the public domain. Two sort of useful links for you to look at. One is the TIFR website, which actually tells you how the progress of the mission is. But the mission is actually going to be constructed around these 4 broad areas I mentioned before. So computing and simulations, quantum communication, sensing metrology, and quantum materials and devices. And the idea is that all of these are going to be separate hubs, which means they will have a centered sort of focused location, but the operation will still be distributed, but there'll be sort of one main location and also a central hub for synchronizing the activities of all of these things. And if I remember correctly, last time Professor Ashutosh Sharma talked about this in an interview. This might actually be also the center for lots of commercialization activities. It might be like a technology park as well. And the model which is going to be followed, and this is sort of important to keep in mind, is this hub, spoke, and spike kind of model, where each of these 4 areas will be a major hub. There will be distributed spokes, which are like small centers, which might solve a particular problem of interest for the hub. And then further, those spokes, or directly from the hub, you could have these what are called spikes. These are essentially sort of individual or small number of PI projects. This is sort of roughly the plan of how this mission's funding will be sort of planned and given out. And one really has to look at where we can fit in and what are the different areas we can perform. And the reason for this is that every research project, whether it's at the individual PI level or a small center level, it's all connected to the overall main goals of the hub, the kind of deliverables which they are supposed to do, the kind of progress they have to make. So everything becomes sort of channeled into the hub itself, and that's where the collection of all the information and sort of recording, I think in terms of the logistics, I've heard the phrase being used as mini ministries. So there'll be a lot of power to sort of reappropriate funds, move the budgets around. A lot of flexibility is being planned for these hubs. And all of this should happen based on an open call once the mission is launched. Based on this newspaper article, the announcement is supposed to happen anytime soon, supposedly next month, but we'll see. The COVID has really slowed things down. And this is sort of a tremendous opportunity. There's nothing of this sort, I think, which has happened in the past. The magnitude of the funding which is being planned for, the scale of the operation, the relevance and the importance of this area, and the fact that, at least we are not too far behind. I mean, yes, we are still haven't had the 20, 30 years of work which has happened, say, in the Western world, in Europe and in America particularly, but we are not so far behind that we actually cannot make an impact anymore. And many of these are going to be strategic technologies, so it will be very important to have expertise here as well. So just to now finish up, to talk about what's going on in TIFR and the DAE system. TIFR and DAE were generous enough to fund the first superconducting lab to me about 8 years ago, with sort of an initial outlay of about 6.5 crores. For the first 5 years. And as Satya mentioned in the beginning, we have made some important new kinds of ideas. These experiments were more on sort of looking at new alternate ways of doing things when we were sort of small. Now with more funding and collaborations, we are now becoming more ambitious, and we want to now build processors and look at bigger projects. And we already have collaborations with Professor Manda Deshmukh and Kedar Damle and Manas Kulkarni at ICTS for theory-related things, but we've been talking to many other people in TIFR as well. Professor Pranab Sen is a resident expert on quantum algorithms, and in 2013, he published a paper for a new type of communication protocol, which is actually testable using today's technology. And in fact, Pranab has been bugging me for many years now, and others now as well, to try some of these things out. But we just overloaded with many things to do, and we have not gotten around to doing that. But hopefully, we will do this very soon. Now, going outside of TIFR, there's a very big group in HRI Allahabad, sort of led by Professor Aditi Sen, Ujjwal Sen, and Arun Pati, which is the Quantum Information and Computation group, which is probably the biggest sort of theory group with lots of postdocs and students. And over the past several years and maybe even decades, they have made lots of important theoretical contributions to quantum information in communication, computations, and foundations. And they are part of all the new funding efforts as well, and are working on important problems. And of course, there are other theory efforts in places like ICTS, IMSC, and some new experimental explorations in TIFR Hyderabad and also BARC. Since about a year back, we have been talking to BARC about starting a collaborative effort to do things. So just a highlight of new developments, Professor Sushil Majumdar has actually initiated 2 activities in this area. And the reason I'm highlighting this is that we need more people to do this. This is not his core area of expertise. He's not worked in quantum technology in terms of quantum information and computing before, but the technique and expertise he has in the experiments he does are very easily adaptable. And I think we need a lot more of this happening to really ramp up the activities in the system. And he's actually developing these nitrogen vacancy centers for creating heralded single photon source for communication experiments. And they have had some preliminary results which indicate that things are sort of going in the wrong way. This is all fairly new. I think a lot of that has happened during the pandemic itself. And they've also actually done a communication protocol experiment, like the first steps of that. And they have gone to the NCRA campus to have a sort of a free, big enough free space to set up the communication link. And they have observed, the qubit 0 and 1 state with good signal to noise ratio. And Sushil has been talking to me for a while, and he's now also been talking to other people around the country. And this is really exciting to see that this work has started now. So really, what's next? Now, the problem is that the current team size, I'm now really talking about TIFR, DAE, in the context of what we need to do about this mission. And there's been an ongoing discussion for several months now on how to go about it. So one, of course, obvious thing to do is we have to hire new faculty. We have to somehow figure out the way to attract the best in the world to come and join our efforts. In the last 4 or 5 years, we had some good candidates, but we are not able to turn that into successful hiring. And we need to do this not just in TIFR Colaba, but all across our centers and units. And one real challenge, I just want to sort of mention this because this is going to come up, that they often don't fit in standard departmental structure. And we had one particular case where we lost a good candidate because 2 departments couldn't think that they would fit in here. So we really need to think of new mechanisms to address such hiring. And we have to also figure out, this is I just mentioned in the context of Sushil, that we need to incentivize or find a way to excite them. I guess a lot of the onus will be on people who are already in this field, but also maybe from the side of the system to incentivize existing researchers who are in allied areas, that they have the techniques which they can adapt. And part of the goal of this talk was to expose you to these different techniques which are out there. And you might say, aha, I know how to do this. So maybe I can work in this particular area. Of course, people are busy with their own things. And so this would require, time commitment. And this is sort of the usual things, but I thought I will add it. We really need to do something to simplify administrative procedures to speed up establishment of new research group. It doesn't apply specifically to this area, but it's very important for this area because the amount of effort, scale of operation and funding that's going to come in we cannot be bogged down by this. And I'm just appalled at this this new rule on these restrictions of global imports. I'm sorry, I have no other word, but I thought after a few months things would simplify. It's been 1 year, and so much money was funded to this 50 groups across the country, and very little money has been spent because we're still figuring out how to do this. How to import things and going through this procedure. So I if there are any,
yeah, that's called interference of some sort.
Sorry,
that's called interference. You're suffering the interference.
Yeah, but it's like a even more frustrating problem. Usually we don't have money, and now there's so much money and we're just not able to even spend it. So, and I thought I should use this forum to make an appeal to the heads of institutions and other administrative bodies here to please trust your scientists and let them do their thing. And we just cannot afford to miss this boat, especially when there's such a big and grand plan to move India ahead on this path. And the last point is, within sort of the TIFR DAE system, we need to have some kind of a structure so that we can come under that and conduct research in quantum technologies. And I don't have to belabor this, but we have lots of strengths in our system. There is expertise in superconducting qubits and algorithm. We have a vast amount of expertise in material science, so a lot of that can be adapted. Of course, quantum condensed matter theory and mathematics has been very strong historically. A very unique capability is the instrumentation. I cannot stress the importance of high quality instrumentation that will, the role it will play in actually making these technologies. In fact, a quantum technology of any kind is going to be 99% classical high-end instrumentation. And that has to be done very well for that tiny quantum part to do its job. And we have so much expertise, in INO, and I've talked to many of these people, and they develop all these fantastic detectors and data recorders and analyzers and things. All of those are very easily adaptable for many of the quantum technologies that are coming. And we have, emerging expertise. New people have joined in quantum chemistry. I've been talking to Ravi Venkatramani about thinking about algorithms for applications in quantum chemistry, trapped ions. Saurav has recently joined us, and now with Sushil taking up quantum communication as well. And of course, historically, we also had expertise in NMR, so they are familiar with a lot of these techniques, though NMR as a platform itself is now mostly sort of academic interest. It's not considered a scalable technology, but people are still making new breakthroughs there as well. And of course, we have huge and strong experimental programs in nanotechnology, low temperature physics, and optics, and semiconductor physics, and chemistry and biology. And you see that every kind of this expertise in this area does go in to building these sort of quantum technologies. It's a very interdisciplinary field, and we need to do something to somehow bring all of these people together. And of course, TIFR and DA, we have a history of handling big projects. So we can say that we know how to handle these things well. We have the in-house knowledge and experience to do that. So sort of keeping these things in mind, Director TIFR has put together a small team. This is not any kind of a final team or anything. We just had a meeting a couple of weeks back. The following people attended and sort of just discussed how to go about doing this. And that was the reason I thought I would use this platform to sort of invite all of you to think about this. Come talk to me, send me an email. We are planning for some activities under this new umbrella so that we can have talks from the experts in all the different fields we have talked about. And we have to do it differently. There are lots of talks available online. We can go and listen to them, but in a way that where it's really a sort of a pedagogical, and we can have interactions. So Jaykumar is sort of leading this effort along with me to get this going, and hopefully, and the director has sort of promised that he will support as much as possible to really sort of create a framework under which the quantum technology activities under the TIFR and extended DAE family can really go ahead in full force. So I will stop here, and I hope you will take my invitation very seriously, and I hope to talk to all of you in the coming days and weeks. Thank you.
Thanks, Vijay, for really very comprehensive talk, not only talking about the technologies and what is in future, but also the strong message of bringing the so-called more classical technologies to kind of come into because most of, the way you said, more than 90% of the technology is something which is classical. I think that's a good
Absolutely.
transit from the current work, of course, given their bandwidth and given the existing commitments and so on. But nevertheless, I'm sure there will be lots of questions. So let me not take more time. Let me first go to Professor Vivek Datar, because he was, I think, waiting for some time. Yeah.
Can you hear me, Vijay?
Yes. Yes.
Okay. I have two short questions. One, namely, you talked about half a dozen systems which have been used all over the world to construct these qubits. Is it true that just like you have ion traps, you also have electron traps? Why is it that electrons in traps have not been considered, or have they already been considered by people and there's some issue with them? And the second question relates to, what do you think is the best area where we can make a mark in quantum computation, or is it in quantum communication, or even in sensors? What is our best bet? Or is it that right now we are at a level where we cannot really say what is the best bet? Or
Okay.
what's the best area?
Let me take the questions one by one. So just a clarification here, when you said electron traps, do you mean like free electrons, like in
Yes,
vacuum?
that's right. Because for instance, free electrons can be trapped for months.
This was there are experiments actually where I think some of the quantum jump experiments were also done in those kind of systems following the early work on trapped ions. But yeah, that's a good question. I have actually seen some papers, but for reasons I don't fully understand, it's not those kind of free electron based experiments have not really progressed that much. What has happened, of course, is the quantum dots approach, which is a 2D electron gas, sort of an effective electron. There was a proposal maybe about, I want to say, maybe 15 years ago of electron traps on the surface of helium. So basically, you have an electron which is on top of the surface of the helium, and sort of the interaction with the image charge allows you to create sort of a stable trapped electrons. And this proposal came out from actually a couple of groups collaborating when I was finishing my PhD. And then there were some experiments in the lab of Professor David Schuster at University of Chicago. But it's been slow going. I think it's a very complicated system, but when they analyzed it theoretically, it had some fantastic properties. And they were going to use like motional modes of that trapped electron as a qubit. But I understand what you are saying is that if we are able to just trap an electron freely, then we can
much in
apply
the manner of trapping
field.
ions, you also can trap electrons. They should be simpler.
Yeah, what might be maybe challenging is that how do you then control them? Because the Zeeman splitting is basically the states you're going to use. You're going to apply a magnetic field and create spin up and spin down, and then those would typically be in the gigahertz regime.
Yeah,
and maybe the two technologies are not completely compatible. But this has not been very popular, at least so far. But I will look this up again and maybe send you an answer offline as well. But yes. The only in the context of this electrons and helium, I know about this. The second question about which of these four broad areas are you talking again now specifically for the
for the Indian context,
Indian community?
We
don't have a choice per se. All those four have they have interconnections and they have their own pros and cons. I mean, clearly secure communication has very important implications. And so that is going to happen, and that needs to happen. And in fact, it's even worldwide, it's probably the most advanced quantum technology of the second revolution. There are many commercial companies which can sell you these and set up these QKD links as well, and including a company in India which has been around for a couple of years called QNew Labs, and they're offering such solutions. The question always is, do we really need it today? And there are no easy answers to that. One particular thing which has sort of caught my attention and has been used a lot in the last couple of years is that even if a quantum computer powerful enough to crack Shor's algorithm is, maybe years or decades away. There are some secrets which have to be protected for maybe centuries, or maybe at least 100 years. And one of the things people are worrying about is that if an enemy is intercepting secret messages and storing them, but not decoding them, because storage is just so cheap and easy today, that if you're able to do that, and then 20 years down the line you're able to decode it, there could still be implications of that. So it is important to think about alternate technologies which are secure beyond what is possible now, and with the advent of quantum computers in the future. So I think in the context of what area of expertise is more stronger in India, I think there is no one particular case. We have very few people in all the 4 areas. And it's been increasing in the last few years, and the new funding programs are at least exciting people, but it's been slow in getting the funding to be sanctioned, and now it appeared right in the middle of the pandemic, so it's been a little tricky.
Okay, thank you.
I would say we have to go for all of them.
Okay.
And again, the expertise are sort of slightly independent. For example, if I have to suddenly start an effort on quantum communication, it's going to be not that different than somebody starting fresh. So just because I was in a different area of quantum technology doesn't make me necessarily go faster.
Okay. Vijay, there is a question from Amlan.
Hello, Professor. Yeah, thank you for this wonderful talk. This is Amlan. So I was wondering about in the initiative. So what are the scope in which startups in India can benefit? As you probably already know that we are a startup in India. Maybe this is also an advertisement and an invitation to check our website. We are qpiai.tech. We are an Indian startup with ambitions to build commercially viable quantum computer in future. So looking into really a long shot. Yeah, thank you.
Hi, Amlan. Good to see you. So for those of you who don't know, Amlan was a PhD student here at TIFR in Professor Sandeep Ghosh's lab, and he recently joined this quantum startup. I have spoken to several people, and including, we had discussions with your team as well, that, there are not very clear pathways for startups to apply for funding. And from what I know about the quantum mission being planned, that this is going to be a very integral part of this. There will be very strong support. In fact, the emphasis is on commercialization. A lot of it is on commercialization from the beginning, so that the links are created, and the ability to support R&D at startups is also being considered very, very strongly. So hopefully the mission will do this in a good way, so that this particular problem is solved. I mean, in all the consultative meetings we had regarding the mission, we heard the same sort of issues. I mean, I can tell you from personal experience also that often scientists in academia are reluctant, including me, to interact with commercial entities, with full force. And that, I think it's an idea of just a question of culture change, and as the things move to a different model, I think this will automatically happen. And I really hope the national mission will address this properly for the case of startups, at least in quantum. But just from the advertisements by the government and from the office of the PSA, there is a huge effort to help startups. Now, whether this is mostly talk, I don't know, but at least in the discussions I was involved in, this was very, very seriously taken.
Okay.
Thank you, sir. Thank you.
Vijay, there are quite a few kind of comments, and maybe you can read in the chat. I'm not reading them. Okay. That is something everybody can probably read. But by the time, let me take another question from Vivek Polshetyar this time.
Yes, Vijay, I'm just following up with the question. So one of the challenges that I will see in the material synthesis, like having a one defect in such a huge particle. like these vacancies, the color centers. But
Yeah.
there is another way in material science which we use generally. These are called quantum materials or quantum dots. These are very small nanoparticles of say cadmium selenide or something, and
Yes.
they also have the ability to harvest the photon, create the exciton, localize, 1 nanometer. We use those hot electrons for other purposes, but
Yes.
why everyone is focused on these N centers in the diamond rather than exploring the other color centers, materials?
So from what I know about quantum dots which work at optical frequencies, the issue is mostly related to coherence. Usually the coupling to the environment is very, very strong. And then, those particular states which are involved are not very coherent. So they will decay very quickly. So then they are not directly useful for quantum information per se. What happens usually is that a combination of microwave transitions and optical transitions allows you to manipulate the microwave transition, which is protected. Will have a smaller matrix element, as a smaller coupling to the environment, or might even be protected by selection rules. And then they can have long coherence times. So optical levels, levels which are separated by optical frequencies usually have lower coherences. I mean, at least I know from a little bit of reading about that. There is really no, apart from coherence issues, there's no other restriction. Usually, a lot of this happened by familiarity. People are working on a particular platform, and then they realize that, oh, okay, this has all these nice properties, so let's do some quantum stuff on that. And there's a lot of scope for that even now. I mean, just today, I got to know about a work where they made a new type of qubit. This actually came from my PhD lab, which combines, it's actually a semiconductor type qubit, uses Andrea bound states in a superconductor, but uses the superconducting techniques to manipulate them. The coherence times are terrible. I mean, like compared to what well-established systems are, but it promises sort of a new platform with some potential advantages. So, and there is no reason why a completely new platform can take over the field in the next couple of years. And I think that's also a place where a lot of scope for innovation is there. So if you have ideas, and of course, you and I have spoken about some of the things you are trying, and we should continue to do that as well.
Yes.
But yeah, regarding the optical quantum dots, that I think is the answer.
Okay, thank you.
Yeah. So Vijay, so you saw the chart on the Zoom, but let me go to YouTube, and of course there was a comment from Ravindra Sinha. I take your invitation very seriously. You have done good job in giving an overview of QT, not available on anywhere in on this form. But the question is from Abhinav Chaudhary. It says, can quantum computers be used for simulating our universe at the smallest scale, that is Planck scale? Can it reveal many secrets of sub-Planck scale physics?
Okay, well, my general answer is that people are exploring all aspects of all problems where quantum mechanics plays a role. Now, if you're going to the Planck scale and we're talking about quantum gravity and things like that, then I'm completely lost there, because I don't know what can and cannot be mapped efficiently into a quantum computer. Of course, in popular talks and in advertisement, people will make you believe that the quantum computers will solve anything and everything for you. Except that we just don't know how to do it just today. But yeah, I don't know. Maybe if anybody from the string theory community is here, Sandeep Trivedi, if you're here, you want to say something about if you're aware of such efforts?
Spenta is there. Sandeep,
Or Spenta? Yeah, Spenta, I was there. I saw Spenta.
No, I'm not aware of any such efforts at the moment.
So definitely high energy physics simulation. In fact, there's a talk in one of the new IISc seminar series on high energy physics simulations using quantum computer. But yeah, I mean, the possibilities are just many. It's a very hard and non-trivial thing to do, which requires people from very disparate fields to talk in the same language. And that's been part of the challenge. And some countries have done it well by creating the right kind of platform. And I think we need to do the same as well. I mean, it will be difficult for you to convince me to go to and have a discussion with string theorists with some nitty-gritty details, but I'll have to try.
Okay, so are there any questions? Any more questions?
Satya?
Yeah, GRK. Yeah, go ahead.
I just want to, well, not about the scientific and technical. I think I enjoyed it very much. But Vijay made this point about something that affects, I think it's going to affect all of us, across quantum or non-quantum. We have to do something. Spenta is there listening. Many other people are also there listening, but it must be said. You cannot give 8,000 crores and tie our hands down with all sorts of procedures. I wonder how even the 200 crores will be spent, because now if Vijay is inviting people and everybody is getting, excited about it and they want to set up labs, and for everything above 5 lakhs, you take 1 year to get materials. It is actually, it's totally frustrating and completely counterproductive. I don't know what can be done. More than quantum computing right now, I think we should worry about this problem. There should be an extended seminar on all these things. And we must find a way, not just a seminar, we must find a way. I don't know what can be done, but we have to break this. Otherwise, it will just remain a dream. One more idea, one more promise. The government gets the headlines, 8,000 crores given. But then they'll say, oh, the scientists didn't use it. You didn't let them use it properly. How would they do anything?
No, this is why.
So that's my rant. I'm sorry.
I mean, I have been fighting this for the past 1 year. I've tried in my own ways to take up this discussion, but very little has happened, and even what has happened is being implemented with inconsistent policies across the country as well. Like every institution is doing its own thing. So the same two people could be trying to buy the same product, but one person gets the waiver, the other person is just waiting for a long time. It's just a tragedy. I have no other words for that. And I completely agree with Ravi that if we don't fix this, and I have mentioned this many times in my discussion, that if not for everybody, such a gigantic effort cannot be derailed by this policy, because there's no simple solution for this. You're trying to develop quantum technologies in India, indigenize it and have the expertise here. But to do those experiments, you need, imported technologies. So where do you draw the line?
Vijay, I think just one more thing. For institutions which are working at the cutting edge in new areas, which the country wants to develop, there have been exemptions. And I think we should try that route, because BAE, Department of Space, and perhaps DRDO, these are things which are very crucial for the country, and they cannot be tied down by procedures which are meant for, a whole array of things. And I wonder how you will lose sleep over what to do.
No, I
don't know. It's frustrating.
I will make that call whether I want to lose sleep over this particular problem or not.
Anyway.
Okay. Good. Yeah. Thanks, GRK, for the comment. So Vijay, I guess there are no more questions. So
yeah, please, feel free to email me if you want to know more, and hopefully in the new sort of initiative we are going to get going, there'll be more opportunities to learn and also discuss on actually how to go about entering this field and where contributions can be quick and to take up these things.
Yeah, Vijay, there is also a kind of comment. If you want to take it, this is from Piyush. It's on the chat. Do you want to read this, or you want me to?
Yeah, sure. I mean, there are, it says on the issue of physics of simulations, there is some evidence that even simple looking problems of approximating the ground state energy of a general local Hamiltonian would be hard, even for a quantum computer. I mean, I don't know specifically about this problem, but not all problems are easier on a quantum computer. There are many known problems which even a quantum computer, at least currently, there are no known solutions. So this is not some magic wand which solves everything for you. There'll be many such problems.
Vijay, can I make a suggestion? Actually?
Yes.
Yeah, so one thing that occurred to me amongst many others, many of them I don't want to talk about, but one thing is that it would be good to start some sort of set of courses or something to, build your own constituency type. When you start something new, a collection of courses actually. Yes. Given by many different people with different expertise, very carefully sort of designed, which is, I think, very important for this initiative.
Absolutely. No, in fact, this is one of the things which is being considered. In fact, if Jayakumar is here, maybe he can add a comment. He himself is very keen that this should be one of the first things we should do as soon as possible. It's definitely on the cards.
Okay, thank you.
Chandra, do you mean something like TIFR and IIT Bombay would offer masters in quantum technologies or something?
Something like that, yes. I think also maybe you can.
That would be a lovely idea.
That's a great idea. It's a possibility, yes.
We need to build up human resources. I think that's the fast way to get there.
Jayakumar want to say something?
No, Jayakumar.
Sorry, not at the moment. Maybe.
Okay. Okay, then I think we have already. I mean, we're close to 6 o'clock. That's 2 of the 5 o'clock.
Thank you for being patient.
There is not a moment of dullness here in this whole thing, and it has also instilled a lot of nice discussion and introspection. So with that, thank you very much, Vijay, for a wonderful talk, and thanks again for all of you for not only joining, but also I think opening up nice discussion. I hope it will also lead to solutions not only to Vijay's lab, but also maybe a bigger questions will be kind of tackled in the way. Thank you. Thank you once, sir.
Thank you. Thank
Thanks
you.
a lot.
Thanks a lot.
Great talk.